With layer for radiation tube, I move gravity very near the limit explanations. It's just the topics of this function.
You're going to be in office number 2. So if you want to find Louise, yes. All right, and then we can move on to our second talk. So this is the second part on wave modeling for data analysis. You heard Maria's talk yesterday, so Geraint's going to continue on from that this morning. And I should also remind you, if you have any questions, please just interrupt during the talk. We don't have to have this formally at the end. So if questions come, please. Over to you.
Yeah, so it's wonderful to be here. So thank you for the invitation. As Patricia said, this will be a continuation in some sense of what Maria was talking about yesterday. So we do aim to build a part 1. It is impossible to cover all the work that's happened over the past 5+ years, but also the historical context, etc. So if people aren't cited or have got the citations, not on purpose, it's just a huge lot of work over the past certainly 10, 15 years. The slides are deliberately ambitious. I say that because there's more material than I can basically cover, but I think Davy's got these slides uploaded, so it's a reference point forward. So if I'm a bit like in certain slides, don't worry, it's just there to that's the structure of certain equations, but I won't go into detail, but that's okay. So really is a broad introduction to some aspects of numerical relativity. Because of some time constraints, there won't be so much emphasis on the methodology, have some emphasis on the codes and the basic physics implementing some of the coverage. We will also mention surrogates of useful modeling in a sort of broad brush sense, and then also introduce the effective on-body framework, what UV actually means. So at this talk, I'm mainly going to be focusing on inspiral measure breakdown models. All the methods I sort of mentioned here can be applied to other sort of binaries, such as scattering, sort of encounters, unbound orbits, and so forth. But the reason I'm going to focus most of my results on IML models is simply that these are the binaries that LIGO and Kagra are seeing in the these heavyish binary black holes. So let's talk about those. So this is similar to the plot Maria showed yesterday. This is the standard strain for a binary black hole, and it's sort of decomposed into a number of different key regimes. The first regime is the in-spiral. This is where the two black holes are sufficiently far apart. They're sort of orbiting each other, making gravitational radiation. This sort of carries away energy and angular momentum from the system. The binary shrinks, and this means that the frequency slowly increases as the in-spirals. This is a nice regime. We can sort of tackle this analytically. We can do, for instance, these perturbative expansions, the Einstein field equations, in terms of powers of velocity of the speed of light, the Newtonian expansion, and everything's well behaved. However, the problem is that analytical approximations will begin to break down. So as the binary in-spirals, the velocity becomes comparable to the speed of light. Your perturbative expansion breaks down, your expansion some parameters in the order of unity. And this means we need to appeal to other methods, such as numerical relativity, to really sort of capture this sort of late in-spiral plunge through to the sort of merger and eventually the ring down. The nice thing is that the ring down itself is moving sort of again appeal to things like black hole perturbation theory to understand. But you still need information from numerical simulations to essentially set the initial sort of conditions for your ring down. So the geometry of the merger is really what will dictate the structure of your ring down signal. And there's all sorts of different methods we can apply to this problem. We have things like first Newtonian expansion, a lot of recent work in terms of scattering amplitudes, gravitational cell force, sort of effective field theory methods, the Minkowski expansion, expansion in terms of G rather than velocity. The effective on-body framework is sort of an overarching framework that sort of combines many of these different approaches, same as non-neutral waveform models. We have numerical relativity, which I'll also discuss in a bit more detail as well, which again sort of covers the whole sort of picture. We have black hole perturbation theory, as I mentioned. So what we're going to focus on in today's talk is really these two sort of sectors, numerical relativity first, and then eventually discuss the basic aspects of the effective on-body framework. So moving on, numerical relativity. Why numerical relativity? One reason that's always given is that you get complete space-time geometry, you get the full dynamics, and you get the emitted gravitational radiation all in one. And you get this in the full non-perturbative sense. You really solve the full nonlinear Einstein equations without approximation. But as always, terms and conditions apply. In reality, when we say without approximation, there's all sorts of subtleties that come into play. That means we're not really treating the full system without approximations. And these approximations can be, for instance, imperfect initial data. Initial data for binary black hole systems is not perfect, it's not complete. You still have junk radiation because it's an imperfect characterization of the initial binary. You have to impose some sort of numerical scheme to your partial differential equations. There's certain assumptions, such as your finite difference stencils, how you do the time integration, etc. These do contain errors, and these errors can become important. There's been a lot of recent work in terms of how we actually do the extraction of gravitational radiation, especially in terms of things like the DMS frame, making sure that we work with gravitational waves in the correct frame, and so really getting the gravitational waves at future non-infinity. So a lot of recent sort of work is focused on things like the Cauchy characteristics, extrapolation, and so forth, which I won't really discuss, but it's just something to be aware of, is there are intrinsic errors in the American relativity. It's not perfect. But it does allow us to probe the motion rate down, which is something that we can't really do with analytical schemes, but we can do with formal numerical relativity. So all the kinetic ion models today do use numerical relativity to really construct these models. So it is I should say, it is a crucial aspect to model our compact binary coalescences. As I just mentioned, obviously, PN expansion breaks down to be comparable to C, and black hole generation theory does require these inputs NR. For binaries, we'll nearly always talk about the 3+1 decomposition, and we essentially reformulate the actual field equations Cauchy column plus some constraints. I say 3+1 explicitly because numerical relativity is really more generic than that, and you can construct other formulations, for instance, 2+2 scheme, so yes, further time like space like congruence and so forth. But here we really always refer to 3+1 for black holes. So you start from the Einstein field equations as a system of 10 coupled nonlinear second order PDEs. Here they are, as you will know. And you really want to reformulate this problem in terms of an initial boundary value problem. So this just means you look at some evolution system in terms of some generic functions, and you have these derivative constraints and so forth. And what you're really interested in doing is finding certain initial conditions, initial data, then evolving this point in time using a set of evolution equations. So this is the typical picture that we often see, where we're evolving from one hypersurface at a fixed time, sigma naught, so code in time. And so it's nice decomposition of these spatial hypersurfaces, and we then evolve over in time. And this is typically what we refer to as 3+1 numerical relativity. And your constraint equations really are defined on this initial hypersurface. And I've added a few slides just to discuss the initial value problem as well.
Sorry, maybe one detail you wanted to say is that all those derivatives reconcile the spatial theory.
Yes, absolutely. That's right. I've added some slides at 3+1. I'm not going to go through this in detail. This is like if you want a reference point, please look at this, just to find some of the sort of basics, just for everyone's sort of on the same page. As always, notation is widely different between pages and books, so always sort of take care. Sign conventions as well is a real pain. So conventions, notation, always a problem. The key point is that you can reformulate the actual field equations to do with 3+1 decomposition, and you get something known as the AEM equations. These are the AEM equations in sort of your form. The point is you can sort of have these evolution equations for the spatial metric and the evolution equations for intrinsic curvature. And you also have a system of constraint equations. So these are the constraints that need to be satisfied once you reach hypersurface for a physically moving system. And this means you also have a set of evolved variables and free variables, in this case, the lapse and the shift vector. But you also have other evolution equations and full constraint equations. So again, we'll spend much time on that, but it's there for reference. One of the key problems we have in numerical relativity, the ADM equations themselves are not well posed. Really wants the notion of strong hyperbolicity. And what happens with these weakly hyperbolic systems of equations is that small errors really amplify the constraints and this leads to sphere instability, so your code will crash. And this means you just can't perform long-term stable evolutions. There was a lot of work historically to understand why these issues occur in ADM. You get things such as these mixed second derivatives, the spatial metric, and the Ricci tensor. These terms over here, and these really sort of break the elliptic character of these terms. And this really sort of prevents hyperbolicity.
So in mix, you mean space-time or space-space?
So like this, space-space, yeah.
Even space-space.
Even space-space, yeah. So if you get rid of this in the S, then it looks much more like some of the partial type term. And this seems to restore the elliptic nature. So a number of the schemes, such as the BSSN formulation, etc., are really ways to introduce counterterms that sort of essentially help restore some of this nice structure. So a lot of mathematical properties is to understanding what is the principal part of your system of equations and so forth. Other issues that we tend to encounter are things such as coordinates are arbitrary, and there are many bad choices. This is certainly the case. For instance, if you choose G is exciting, you find that your coordinates tend to just fall into the black hole, which is a problem on a finding numerical domain. So if you have numerical grids, you leave it evolve, and your grids just slowly fall into the black hole, which is a problem because eventually it's a singularity and your code crashes. So many bad choices for coordinates, and a lot of work needs to be done to understand what are good gauge choices in order to form these long-term evolutions. Black holes have singularities. You want to obviously mitigate or circumvent this. Many different choices. One framework is known as the moving punches framework. This is a sort of nice scheme in which you can sort of factor out the behavior of singularity and choose certain coordinates that have to be singularity avoiding. And then we evolve the system of equations. The second choice is you essentially numerically excise the singularity from your domain. You just cut it out of your space-time. So here you need some scheme that essentially cuts out a piece of the space-time from just inside the apparent horizon, and you sort of don't worry about that. Anything that's inside the apparent horizon, causally disconnected, won't be a problem for evolution. And this is typically what you find with things such as the spectral finite difference codes. And so the ethics explanation certainly use this, and it's very popular with the generalized harmonic gauge. So many different methods to tackle this, and many different approaches. Here I've just sort of highlighted some of the key differences between the two main camps that we typically find in sort of binary black hole simulations. The left-hand side is based on finite difference codes. These are your standard finite difference stencils. The right-hand side are these spectral codes. I'll show you what the grids look like in a second. But this is typically sort of BAM, the Einstein toolkit, LaZev, Maya, so the Goddard codes, etc. On the right-hand side, we have codes such as the spectral Einstein code from the SXS collaboration, Spectre, which is a sort of modern rewrite of Spec in some sense. BAMS is a sort of a code that's been developed by Jena, also pseudospectral. And there's all sorts of differences that we find that come into play. For instance, different choices of initial data. I have a few slides in this reference a bit later. A key limitation in finite difference codes is we typically use conformally flat initial data, and the assumption of conformal flatness poses a limitation on the spins that we can evolve, and also leads to other problems such as large junk radiation, and it is generally problematic. Whereas the spectral codes have a much more advanced initial data scheme that does use conformally curved initial data, and it's based on this extended conformity sandwich framework plus superimposed curved shield coordinates. The formulations themselves do differ. This uses a BSN or CCZ4 formulation. BSN is just a conformal essential transformation of the equations, whereas the spectral codes typically use a generalized harmonic system of equations. So it's a nice first order rewrite. Moving punches, gauge conditions, they mentioned singularity avoiding hypersurfaces, whereas spectral codes use excision. Black holes are affected on sort of adaptive mesh refinement grids. We typically use things like Berger-Olinger mesh refinement, whereas the spectral codes probably have a much more complex adaptive mesh scheme. I'll show you what the grids look like in the next slide, so you'll see exactly what I mean. Thinking of things like choice of boundary conditions, how you define different stencils, the time evolution itself, and how you do gravitational extrapolation. So both codes can do this Cauchy characteristic evolution. This has probably sort of dropped off in the sort of past few years. Whereas much more prominent in the spectral codes in the past 2-3 years. But I'm sure it's something that will be picked up as time goes on. So this is what the standard sort of finite difference code grid looks like. So you have these sort of nested boxes. So you have Cartesian boxes that you sort of just move around the black holes, and as black holes evolve, you just update your grids, and it sort of tracks the black holes. There's other things we can do, such as we can use multi-path grids. So here you really want spherical grids in the wave extraction zone because the spherical topology is really adapted to gravitational wave extrapolation. So far away from the binary black holes, this spherical assumption is really quite nice. And you can sort of maintain the resolution. And you have your standard sort of Cartesian grids as you sort of have here on the innermost levels. So these sorts of things can be applied. Whereas the spectral grids, as you can see, are dramatically more complex in terms of how they set up the grid structures. One of the reasons why these are much more complicated is because you need to understand the structure of the apparent horizon. And this is because of how you need to form the excision schemes. And you need to track, for instance, the behavior and evolution of the apparent horizon. And if you don't track this sufficiently accurately, you get things like negative characteristic velocities occurring on the horizon, and this leads to instabilities. So this is why high mass ratios, for instance, have typically been much more problematic in these excision codes, than in the movement functions by the discounts.
So the ICTP codes are using spectral bands. There are actually codes with Cartesian grid behaviors.
That's right, yeah.
Which do not have.
Yes, that's right, yes. These are layer schemes.
Right, that's like Pretorius code,
That's right, yeah.
code.
But I think this is sort of fallen out of fashion. I haven't seen much work.
What are you falling out?
I haven't seen much work in the recent years.
Well, then you haven't been paying attention to what Pretorius keys have to do.
Have they been doing decision?
Absolutely.
Yeah,
The
okay.
collisions that East and Corman have just done in the Einstein's Gauss are used in decision.
Okay. Yeah, okay.
So what does that graph mean? You have some balloon like enveloping both black holes.
So this is the common horizon. So this is the individuals with apparent horizons for a black hole, and you have a common horizon that forms about both black holes. That's the approach manager. Okay. So this is really the point at which you have a single random black hole forming, but it's highly deformed, and then it's all settled into a quiescent state as it evolves.
The coordinates there, the grid lines, do they look complicated? Is that just because of a particular gauge that's plotted here, or is there a gauge? Is there a gauge where this is simpler, or is there no gauge where?
There is a gauge where it's simpler. For instance, when the black holes are sufficiently far apart, these gauge in which the black holes are essentially kept at rest. It's a gauge that tracks the motion of black holes, so keeping relatively fixed. But as it sort of approaches merging, you have to switch this off because things start to get more complex, and this is how it works. So yeah, but things are sort of obligated, you can control things better. But as it approaches merger, then yeah, it's much more complicated. As I mentioned, there's a few slides on the initial data, because this sort of came out in the session yesterday. So I won't go into too much detail, just to sort of highlight some of the key differences. Some of the considerations that go into play are, for instance, you have in standard sort of constraint equations in the previous one form, you have 8 fields you want to solve for 4. And this means essentially determine the intrinsic curvature and the spatial metric on your hypersurfaces. And then one of the big discussions is what's the free data and what's the constraint data. And there's a number of considerations, such as you need to satisfy the constraint equations. You want physically meaningful solutions. You want, for instance, binary black holes. And a choice of constraint data can also be impacted by, for instance, subtle choices in mathematical properties. So different conformal rescalings give different behavior in terms of the mathematical equations that come out. Some of those happen to be sort of nicely behaved, so you have a unique solution to your constraint equations. Others are not. So there's a lot of subtleties in how you actually solve this. In a conformal transverse traceless approach, you start performing a conformal transformation of your spatial metric and a decomposition of your extrinsic curvature. This leads to a conformal system of constraint equations. And this goes back to the work by York, Mahada, and the Schnerwitz, etc. And the first sort of scheme that I mentioned yesterday was this conformal transverse traceless, this conformally flat assumption. Once you do this, there's a number of nice things that sort of come out. The first is that you end up with a much simpler system of equations. It reduces to just these. And there's also a solution to AIJ. So this is derived by Geraint York. This uses outcome condition based on the momentum spin of the black holes. And once you have that, then it means you can sort of decouple these equations. And then you decompose the conformal factor into a few components. This is a solution to the homogeneous equation. So essentially, it says some binding energy between the black holes. So I'm going to call this term alpha. And then you have this puncture field U. So this is the singular part of the system of equations. And it's essentially a correction of the momentum and spin of the black holes that helps to solve the full homogeneous equation. And this means that if you sort of dump this all in, all you're essentially doing is solving a single elliptic equation for U. And as I mentioned, so different choices of the conformal factor really affect the structure of this equation that helps determine uniqueness or non-uniqueness of these solutions. So that was the conformal transverse traceless approach. And your free data really are the spatial metric, this transverse trace that's part of the extrinsic curvature, the trace of K itself, and the constraint data is conformal factor and the factor of itself. That's what you solve for at the end of the day. Alternatively, we can look at the conformal thin sandwich approximation or the extended conformal thin sandwich scheme. In this scheme, you're really looking at taking into account information about the evolution between hypersurfaces. And this is exactly why it's called thin sandwich, is you sort of have some knowledge as to how the spatial metric intrinsic curvature is evolving. This goes back to work by York as how SAIFR code. And this leads to a more complex system of equations. And your free data with the spatial metric, the evolution of your spatial metric, as well as sort of trace extrinsic curvature and the evolution of your trace extrinsic curvature. The power in this particular framework is really that you can specify conformally curved emission data. So it's something that is much more accurate emission data, and something that helps us to extend to much higher spins. So I won't go into that in much more detail, just to be aware that it does exist. In terms of parameter-based coverage, this is a recent talk we spent Deborah Ferguson in preparation for some of the Lisa Red Book, certainly Waveform's Red Book. And it supports all the simulations that are available by the various groups. So these are the big catalog releases. There are other simulations available by other groups as well. Here I show SFS of the Rochester catalog, the Georgia Tech Maya catalog, and the BAM catalog, which is Cardiff, Yale, UIB, and Co. Currently, there are about 5,700 simulations that are available. These give a very broad range of mass ratios, spins, and eccentricities. Non-spinning sectors, mass ratio is less than or equal to 18. The RFQ non-spinning simulations for RRTs, I think a mass ratio is 32, 64, 128. But really, sort of Q18 is where things have been used in terms of calibration for sure. Moderate spins, so this is dimensional spins, typically around 0.8 or so. These are well covered up to mass ratios of Q less than or equal to 8. This includes precession as well. Line spins is really only sort of dimensional spins less than or equal to 0.85. For mass ratios 18. You see that there's some simulations that's mass ratio 18, I think sort of around here, but you see there's a huge depletion of simulations at high mass ratios. High mass ratios is just extremely challenging to solve for.
So can you explain
Yes.
one thing about this? So when you count this waveforms, are they satisfying some particular requirement with respect to outputs? Or like if I look at it, I'm looking at the 15 mass ratio case.
Yeah, so I think the answer is that there's no assumptions on the X requirements. There'll be multiple simulations at Q1 on cities. We haven't told us, say, we have the best data from them. So we do look at parameter space as well, different physics.
Sure.
You notice the SO6 ones are really like density packed below mass ratio 5. And is there something special about mass ratio 5 where it's more difficult above that, or is that just a choice that collaboration made?
This was a choice for the collaborations. This is about 1,500 simulations that were targeted to produce the NR surrogate. So again, we use these 3D type algorithms to preferentially choose points in the parameter space, essentially orthogonally cover fully processed parameter space with NR simulations. And this choice here was just restricted to Q equals 4. They are now running up to Q equals 8. So we'll see this sort of suddenly expand into the next release. But yeah, that's why there's a high density sampling up to Q4 in processing space. Then it sort of just depletes. The focus was really on.
Or maybe they got self-satisfying some criteria.
Yeah, and the other issue that I mentioned as well earlier, the SFF code typically struggles with very high mass ratio simulation, especially with high spins as well. This is going to get really equal apparent horizons, and this means that your essentially mesh refinement needs much advanced methods to help subtract behavior of these apparent horizons. And it's harder for them to do the simulations. And that's why you see the finite difference codes start to really take over. So you see RT at that via starts to correlate these high mass ratio plus the parameter space.
Sorry, another question.
Yeah.
You know, when that second set, the test word number going to mass ratio 8, roughly will be.
I don't know when it'll be released. I think Q8 surrogate is being iterated on right now. So I think it's going to be next year. So it's probably a reasonable timeline next year. I mentioned that errors are perfect. This is a wonderful example of how it's not perfect. So this does actually impact, for instance, your calibration of your waveform models. It is not really systematic. So two waveforms produced in the same kind of parameter space don't necessarily agree. And there's all sorts of trouble that still comes into play. And you can see here, especially for higher multifolds, where you need high resolution, a lot of accuracy, you can start to get some very strange effects come into play. Some of this may be, for instance, center of mass drifts, which are problematic. There's other things such as changes in gauge condition, the merger, and so forth. And this just means you get some unphysical behavior in the amplitude phase at the merger. So different waveforms may be accurate at different points in the parameter space. It becomes very difficult to complex problem to sort of help track exactly which waveforms are accurate in which region of the parameter space, and for instance, to make it accurate in the mean spiral to not merge really down and so forth. So systematics is a genuine problem, and code comparisons are actually really quite tedious, but I'll leave that to a future note. I mentioned that extrapolation waveforms to future infinity is also important. This can introduce unphysical features. Here we have some different extrapolation orders. You see that it changes the behavior of the merger breakdown. So again, choice of extrapolation does affect gravitational waveform that you extract from the NR simulations. Cauchy characteristic extrapolation is something that has seen a resurgence in the past few years. It can help reduce some of the near-zone gauge effects in your waveform. And there's been a lot of work on understanding the impact of frame choices on the waveform. So for instance, using Poincare charges and super translation charges to help fix the BMS frame. And it sort of can sort of help sort of improve the agreement with TN. Yeah, sorry, kind of.
No, I mean, just namely when they see this displacement after peeling down from the zero, one can think of memory effects, no? But these are artifacts, these are not memory.
These are artifacts. These are not physical. This is an unphysical drift, yeah.
So it's impossible to see memory effects in numerical relativity way.
So one of the issues
that would be degenerate with these artifacts. So.
No, it is possible. One of the issues you have is that if you don't do something like Cauchy characteristic extrapolation, you sort of just wipe out the memory effect. So if you try to do extrapolation, then this just wipes out the secular sort of memory effect in itself. So these waveforms here didn't use Cauchy characteristic extrapolation, so it becomes a bit of a blurred sort of discussion anyway. And yeah, you certainly have to be careful as to understanding what the errors in your NR simulation to understand, are you actually extracting the genuine memory effect, or is there some other additional systematic at play? So NR simulations, I think, are not free from systematics, and it really is important to understand what is the systematic errors in the simulation, how to compare to other codes, and so forth.
Well, but there, I mean, it's funny that the UV is also showing no memory.
Yes.
That's what the UV is also.
Yes.
And so, let me just perhaps augment a little bit what you said. If you use Cauchy characteristic extrapolation, we actually one would like to use Cauchy characteristic matching. So even CCE will have things missing. But I would argue that it's not necessarily true that that's the only way. When part of the memory is the problem of the way to calculate the waveform for a finite amount of time. So there's information prior to it, and this is what Boyd and Nick are trying to do, is just add to it very early at the end, and then somehow match to capture it. And okay, once you have that, you could perhaps do away without going.
Yeah, absolutely. I fully agree. And has been working in this direction as well, with recent memory, or including memory in the hybrid surrogates as well. So again, this is in. Yeah, fully agree. Moving on to surrogates, because we're already a topic of talk. We used all our models to sort of jump ship. Our way of compressing essentially a broad way of compressing the number of degrees of freedom into something that's much more manageable. So the schematic approach to this is you first build a reduced spaces using some particular approach to help localize your training data. For instance, use single value decomposition, use something known as the greedy algorithm to help localize your system. This means we're essentially end up with these different sort of waveforms here across the parameter space. You then look to essentially calculate or interpolate projection coefficients of something called empirical interpolation nodes in the time frequency of the parameter space. So to be clear, you first construct a reduced basis, these waveforms. You're then looking for certain nodes that helps characterize key features across the parameter space. So you're looking at these empirical interpolation nodes that really capture the dominant features in your reduced spaces. Once you have these dominant features in reduced spaces, you can form these global fits across the parameter space, and if you have a fit across the parameter space, you can evaluate this at any point in the parameter space, and then use this to help reconstruct the input data. If that makes sense, I'll have another diagram which makes it a little bit better. So you build the reduced spaces. So here you're essentially re-representing your waveform, your straight H, in terms of these reduced spaces coefficients and some weight, as you do inside of functional analysis, as you would do with quantum mechanics, for instance. There's the reduced bases. And you basically chosen such like the training data is represented by the basis within a certain tolerance. So you have something called a greedy error, analogous. This just determines how well can you reduce spaces represent input data. Typically use some data-driven metrics such as quantum mismatch that was introduced yesterday to be satisfied within a given tolerance, typically well below bottom errors themselves. Once you have that, you can reconstruct what's called the empirical interpolant. The empirical interpolant is where we fit these points across the parameter space. That just means you can sort of interpolate this waveform based on your knowledge of these reduced species, which is sort of given here, as well as this little matrix V, which is just the evaluation of reduced species of these empirical interpolation modes. And then you just need a global fit across the parameter space for these sort of coefficients here. And this means that you already have knowledge of these reduced species. It's something you can store in memory, store offline. Evaluate this fit and you can immediately reconstruct the waveform model. The key point here is you no longer need to go through a computationally extensive procedure to evaluate H. You just have these reduced spaces which you calculate once. You have a fit list which can, for instance, be nice causing fit. And it's just an efficient, accurate way to represent and reproduce the input data. So the typical plot that you see goes back to a plot by Scott Field, so this 2013 paper. So here we have just the time and parameter space. And what we first do, as I mentioned, is find reduced spaces. So you divide all these waveforms in red, and find the points in the parameter space and localize your data progressively or greedy. You then have these empirical interpolation nodes. So you find the points in the time space that essentially maximize or find the dominant features, for instance, the peak amplitude, and then you form in fit these across the parameter space. Once you have a fit across the parameter space, you evaluate it at any point that you wish. The current state of the art that I mentioned earlier is NR surrogate at 70 Q4. 70 because it's fully processing, so the mass ratio and 2 spin vectors. Q4 because the mass ratio is 4. This uses 1,520 NR simulations. Obviously, each of these NR simulations can take weeks or months to run individually. But the NR surrogate takes milliseconds or 10 of a second to evaluate, so it's a significant reduction in computational cost. You can reproduce the NR data within a pretty decent accuracy. And this is sort of how it looks. You can sort of just demonstrate that you can, with the NR surrogate, reproduce the input NR data to see that was considered. And this sort of scheme can also be applied to any semi-optical waveform model. This includes effective on body models. So this is work done by Mike Spurrer, Ben Mackey, PhD student Mr. Thomas. So AJ's done work on this as well. So you can just reproduce, for instance, an input UV model with your reduced order model. Shown here. I won't spend any more time on this if there's any questions on reduced order modeling. If not, we go to the effective on body framework. So there's probably going to be more questions on this, I anticipate. This is another approach to body dynamics originally introduced by Alessandro Bonanno and Thibaut de Boer back in 1999 and 2000. And this was inspired by some historical approaches in sort of EM interacting content to body problem, as represented in the 70s, where you can find these effective on body analogs to full two-body quantum problem. And the basic idea of EB is to map the two-body problems. You have your binary two black holes, mass 1 and mass 2, into an effective one-body problem where you look at, for instance, the motion of a test particle, a reduced mass mu, in some deformed space-time. So this is exactly what we're doing here. And we need to find out a way to calculate this deformed or effective external metric, and from that we can get the equations of motion. So the three main analytical components to an EUV model are a Hamiltonian to describe the binary conservative binary dynamics. You need some knowledge or some description of the radiation reaction force, so kind of the loss of energy and angular momentum via the emission of gravitational waves. And you also need a framework to actually calculate gravitational waves in spiral motion and read that itself. Dynamical friction. So if you were to consider a test particle orbiting a non-spinning black hole of mass m, you have some short space-time. You can write down a Hamiltonian. This is something you often do in like grad school. You write down a ranging. You can write down a Hamiltonian for a test particle of mass mu in space-time. You get something that's exactly like this. And from this, you can calculate the effective radial potential. So hopefully, this is something that's quite familiar. And what you find is that you get difference of behavior based on, for instance, the optical momenta. So this is just the effective potential against these separation. So different choices for L. If L is less than the L of the ISCO, circle orbits do not exist, so just plunges. So this is this notion of the effective potential finding this barrier, etc., whether you get nice circle orbits or not. So hopefully that's also really familiar. The problem that's not so familiar is how we actually show you about mapping the two-body dynamics, the geodesic motion, the single particle in this effective metric. So this is how we sort of first break down into action. We have contributions from each of sort of black holes. These terms here really are the line element along the trajectories of the particles. In this time, your standard sort of metric G nu, and this is just your standard gauge fixed Einstein on the action. It's Geraint itself. And the aim of the game is to associate your real two-body dynamics to the effective bond dynamics in this external space. So I'm going to focus on effective action in terms of this term here, but now we really want to work with and consider the line element along a trajectory of an effective particle. So now this effective magic comes into play. And the key magic really happens when you consider the deformed mass shell condition. So there's a really nice discussion in this paper by Demore in 2001. This term Q really contains things that, for instance, quartic and higher order momentum interactions, so P power 4, etc. These types of interactions come into play. And the key one is you can invert this to find the effective Hamiltonian effective energy, just by sort of solving these deformed mass shell conditions. Now, the reason why this is interesting is you can start from sort of the real NPN Hamiltonians, so come to 5PN or whatever you want. So write down the real PN Hamiltonian. Then you write down an ansatz relation between the EOB Hamiltonian and the effective Hamiltonian. And the key one is that this ansatz here, this isn't something that's magical. This is really something that arises from inverting this energy mapping that I showed in slide 4. This is the key trick in the first papers. And in this case, the EOB Hamiltonian is related to your real PN Hamiltonian, just through a different gauge here of transformation. So you can sort of relate it to in terms of these generating functions, where each of these brackets introduces a factor of C2 sort of high PN correction, if you will. And the key point really is that we need to find the unknown coefficients in the effective Hamiltonian by matching the left-hand side to right-hand side. So you should be reproducing the PN dynamics in the appropriate units, etc. That's what the key trick would be. And what we do is we find if we find the effective Hamiltonian in terms of this geodesic motion of test particles deformed external space plane. So now this is similar to the Schwarzschild problem. So I'm just going to consider a non-spinning Hamiltonian initially. So when the reduced mass goes to zero limit, you recover the Hamiltonian for the test particle in Schwarzschild spacetime, so the Hamiltonian I showed earlier. And you find that the way in which this differs from Schwarzschild is that you have high order PN corrections. These potentials really depend on the reduced mass, in this case nu, which is just u over n. And this means you can write down an effective metric that looks like Schwarzschild. You now have these effective default potentials that capture these high order PN corrections that really tell you good information about the two-body dynamics and these potential interactions between two bodies. And this is really the key point for me. The dynamic is encoded exactly in these potentials. So you can see you're saying that looks pretty similar to Schwarzschild. So 1 minus 2, where u, I should say, is the inverse of the radius. So 1 minus 2 over r. So except 1 as Schwarzschild, then you have these high order PN corrections, like information about the two-body dynamics. So that's the non-spinning Hamiltonian. So hopefully I haven't lost everyone completely at this point. We do the same thing again for this deep potential as well. So these are the two key potentials. I should say that there are certain coefficients that occur in gauge potential, such as this A6 term. A6 here represents an as of yet unknown PN coefficient. And one of the key points of the UV is you are able to introduce flexible coefficients in your potentials that essentially capture as of yet unknown PN terms, and you can calibrate these to the simulations. So this really helps, I guess, tame the behavior in a strong field as a sort of approach merger. There is a
So the 5PN is almost known for conservative almost there are but anyway, I mean, even if it was fully known, one does not expect the exact 5PN to match the A6 that is 52-moment relativity because the big, I mean, starting information.
Yeah, I think that's right. Yeah. and then gauge traces.
But those coefficients that go to 5n is known apart from relative contributions.
Yeah, I think that's right. Yeah, we use them in a better than I do.
Is there a reason why this parameter not run? Why would it not run?
Not bad.
It says it function as opposed to a parameter.
So one of the things, one of the things that you do is rather than doing static sets, you sort of do restate. So I think it's like how do we takes in this kind of thing.
No, but actually they do. It's just that from simple orbits you can find a simple local expression. In general, they depend on the energy, yes, in general, but on simple orbit they're
Possibly,
Regardless of the mass ratio.
yes, yes.
possibly with the initial reaction effects is very natural to get there to the band thing. It's just
Yeah, I mean,
it has to come inside because
no, the nice thing is that just specializing in super orbits, you think you get nice local close for one. Otherwise,
Okay. And so if there's spin, you just pick up another potential.
Yeah, I'll come to that later. Sorry. What I mentioned is that there's significant freedom in Hamiltonian. So you different ways in which you can write that as Hamiltonian. This is a particular choice of Hamiltonian. You don't have to use that S-spin, which is mass Hamiltonian, etc. Different choices of gauges, such like important effects, for instance, the light rings, etc. Different information to be included, different choices of resonation, etc. So it's an extremely flexible framework. It makes it kind of tedious at times because you have to follow a lot of things to look at exactly what's going on and how it is from something else. So very powerful framework, but a lot of things to tweak. Resumation is something that is quite critical in terms of reducing the difference to NR. This is something that's sort of I guess in a number of years. So Halley resumation is an effective strategy. This is just rewriting the standards of Felix mentioned Halley form. This is a particularly nice way to do resumations. An example of the resumation strategy adopted in SMART V5. So again, just taking a one-time Halley inserts. So essentially, sort of control the, I guess, extrapolation of your Taylor expanded sort of potential into some higher energies and so forth. I thought I had a lot on it. In terms of including spin, one thing you often see is you sort of take the standard sort of Hamiltonian that I showed before and introduce these gyrogravitational magnetic terms, GS terms, and these are just ways to include, for instance, the lead order in spin information. So you can include spin effects, but again, the choice is not unique. It really comes down to choices of gauge effects. High one include, for instance, spin squared contributions that differ. Something to include spin squared contributions to effective Hamiltonians, which is not true. But it is known how to do this. So to say that is known, you can write down exactly how these gyrogravitational magnetic terms look. And there's a lot of papers. This is not exhaustive in any way. So these are sort of papers that I found particularly useful. So let's take a look at this and see how this works. What sort of information is included. And this is where things start getting a bit messy, which is okay. And it's really just a statement that you can generalize this Hamiltonian to arbitrary spins. So you essentially play the same game. Rather than write out the structural metric, you write out the curve metric. I should say, when I say arbitrary spins, the person is no longer spin aligned. Now has spins that are misaligned with the coordinate momentum to get precession. So it's looking at generic orbits around a curved black hole. So setting things become much more complicated. But you play the same game, which is you can sort of write down your sort of, again, your deformed metric. You can sort of write down all these various potentials in sort of space-time. So you have your sort of Hamiltonian. And from that, you can get an effective precession Hamiltonian. Again, including spin orbit contributions, etc., higher spin terms, and so forth. And you can sort of map your effective metric to some deformed curve background, where again the total spin, so A1 plus A2, where A is just S over M, is really the thing of interest. So this is sort of the image that we're taking. But this is when things are getting really messy. So I don't want to go into too many details on this. Yeah.
Does it mean that since the spin is kind of independent, so now if you go into this effective parameter of the combined spin, and it's aligned with the z-axis, there's what's
Yeah.
shifting frames.
Yeah, that's right. So this is again, you're free to choose this frame choice, but you can choose a frame in which your spin is aligned with Z, and that's typically what's been done, for instance, in these papers by Palmelli and co. Is assume that your Z axis is the spin. Yeah. This differs from the native spin axis that we're interested in terms of the like.
Start with the first general thing, then you think a bunch of things.
Yeah, precisely. So here you look at something where it's aligned with Z based on the motion of the secondary, so part of the evolution of the spin around. Yeah, it becomes a bit of a complicated mess, but it can be done.
If I were to think now, say, of a binary star system, a black hole star system, if I'm thinking here, if I don't go to all the way to 5 here, my neutron star is particle doesn't matter what I do. By trying to map to a Kerr black hole solution, am I not introducing further issues?
Yes, absolutely. So what happens, this Hamiltonian is easiest to look at, just as a what happens when you want to do finite size effects, then you essentially again for the potentials.
Right, but I don't want to, I want to say, I'm going to carry this further, but then I'm going to study a binary star system. If I don't go all the way to 5 p.m., that's a fair game, and I can use point particles to study that. But now if I'm forcing a Kerr solution, well, this trick out exterior to a neutron star is not a Kerr solution. So I'm also introducing some source of error, and I'm not sure what order is it coming.
I'm not sure I can say it's what order it's coming. Here I think this is still a case of reducing to, I guess reducing to a Kerr metric in the U goes to 0 limit. So I guess it's one. I'm not sure if that even makes sense. Interesting perspective. So I have no idea.
Okay.
The sorts of take age and speed present quite a lot of contributions. So exactly what you find. So you have corrections to the A potential and other potential.
So there you wouldn't be mapping to a Kerr solution.
But also speed that effect earlier than 4 p.m.
Right.
Than 5 p.m.
This method of using a different Hamiltonian based on to include the precession, is that what like the current assessing SUV in our models last week did, or because I thought they started from the line spin UV and then just kind of
Yeah, so this is I mean, so this initial work in terms of the metric goes back to some work with more as far as I know. But in terms of the valid implementations, S cannot be fine, but it's very interesting. Does use this Hamiltonian. There's different choices. The S0V3 and S0V4 are based on the test spin limit rather than test mass limit. It's a different structure to a Hamiltonian. And this is so the framework again based on that's introduced by Geraint and stuff that very goes back to. So it's still being present. In where it becomes a bit more tedious, it's a transfer or constructively process rate models go from the in this case the aligned state. So way from the twister to the processing sort of model this is Patricia's framework, and exactly how you do this mapping. So in V4, you did use a genuine processing of Hamiltonian to spin evolution and dynamics. In V5, this is not the case. You instead sort of based on Hamiltonian to get spin Taylor evolution equations. It's fully consistent with the Hamiltonian that you have in V5. And then in addition, we also do actually they have some partial processing information of Hamiltonians, orbit averaging, because the time scale in which processions will definition, action time scale, etc. And you can get genuine processing information of the evolution of the binary influence because that would be processing brain. So where are we? Yeah, so we have probably breaking now on. So before we go to some of the other things, especially fibers for the differences, yes. You just told me how to could be system of equations. You have a Hamiltonian, you do the same thing you do with any Hamiltonian. And this just leads to a system of equations. And this is often why people say that the EM framework is in some sense more fundamental. Not only do you get the gravitational nodes, you also get information about its dynamics. So that is native to UV. And even if you don't calibrate with NR, you still run this measure and run the dynamics, you'll be wrong, you still get a prediction, which isn't true in functional wave models because you directly model gravitational signal. It's actually a real data driven version of norm, whereas UV is more about the the intrinsic fundamental physics. I think that's probably a fair statement to make. So yeah, and this is radiation reaction. The radiation reaction force itself is given by the flux of the angular momentum, and this is expressed in some of these factorized modes in HLN, various recent multipoles. So you still need the description for your gravitational wave modes, and this was given in terms of the inspiral plunge or inspiral plunge ring down framework in terms of these factorized modes. So the inspiral plunge is given by the factorized framework. Here, NLM stands for the non-quasi-circular corrections. These are corrections to wave modes that help account for the near plunge and quantum dynamics, but the wave trajectory is suddenly deviating from quasi-circularity as a function. It has a non-logical description of how this performs. Now, the factorization of each multipole goes back to a number of schemes produced in earlier papers. I think this is the more is Prakash or the more Nagar, one of them, I can find that out. But it's written in terms of a number of different terms. The first is this Newtonian contribution, also helps as a comparative. Then we have some effective source term, which is just again related to the energy, to the even modes, the momentum and velocities in terms of the odd modes. You have the tail terms. I think Ricardo mentioned the tail terms yesterday as well. Here the tail terms we sum an infinite number of the logarithms. So usually does contain these tail terms in orders. Then you have some residual phase correction due to substituted logarithms, and likewise you have a residual amplitude correction. And both residual phase and amplitude are chosen such that if you take those and use a PN and expand them, it does agree with the PN expanded modes. And then we have the AQC corrections that I mentioned, which are non-logical and are purely calibrated to NR. So these aren't really physical, it's just a particular way to help UV smoothly transition to concentric. And then you complete the UV waveform by touching on a ring down. And the ring down itself is given, as I mentioned, by fractal perturbation theory, typically something like some of the superposition quantum modes, or again, some knowledgeable merger ring down model that is calibrated to NR, which is typically the case study in recent iterations of UV. There are two main flavors of UV in the market. So if you sort of go look at sort of valve or some of the analyses that are done, you'll see SUVNR. This is sort of the AI model. This is really Alessandra and co. And you have TB-RESON-S, which is really sort of collaboration between ICTP, Curie, and Yena. This is TB-Law, Alessandra Nagara, Sebastian. You can see it really developers. And there's a huge number of differences between the two. So this is this really nice summary table in this paper by Mohammed Khalil, as part of the V5 paper release. And it really details some of the key differences in terms of different physics choices that are made and different models. So SNR-V5 is the latest generation SUV model on the market, and TB-RESON-S, which explains that the current state of the art of the TB-RESON-S model, there isn't so much a versioning, there's naming conventions. The TB-RESON-S Giotto is the latest state of the art, and this is what this corresponds to. We can just go through and sort of look at the differences in terms of the information that's included in the non-spinning sector, differences in the A potential, for instance, and so forth. We can do this for each of the different sectors and just look at what are the key differences. I won't go through this in detail because in 5 minutes, it's all on the slides.
So I'm going to ask you a question, a real question. Can you tell me the S and the T, just the terminology? But also, am I eventually supposed to think that a Vn would be thrown away in front of a Vn plus 1? Okay.
Yeah, essentially, yeah. So it gets a bit messy. So the T in this case that's the tidal. So tidal EUV reason because it is particular estimation of goals and estimation strategies and X is spinning. Same for SUV and S stands for spin, NR stands for the calibration, and you can also get S1 or T and 5T, which just needs a tidal information to it. So in terms of V4 to V5, this becomes a bit difficult because V5 is like the next generation of V4. It has a fundamentally very different Hamiltonian structure. It's not like a natural progression of, oh, we just need more information, more calibration. It's a genuine sort of jump. So they really are sort of getting parallel models that are fundamentally different. The V5 is state of the art, older generation, but there's still differences that are interesting. Intrinsic load, I should say. So V6 may be completely different again, not in that progression, or V6 may just be V5 plus 1 again.
You
You already said this, but I just didn't want to make sure. So for this table, we're saying V5, does this mean that the actual evolution follows the evolution of the effective particle and the evolution of the effective spins instantaneously with no sort of approximations of the system units?
I think that's right, self-consistent, yeah, that's right. Yeah, sorry.
All of these things are based on the post-Newtonian expansion with resolution. Is there any obstruction or Boltzmann constant?
No, so this comes down to the statement I made earlier, which is this is purely focused on anything that works quasi-circular. I think people haven't yet figured out how you really sort of include the PN information with circular models in a self-consistent way. The most recent work has been by Mohammed Khalil. He does construct a Hamiltonian exactly these hyperbolic encounters, but they do include some of this cosmic information. So there are ways you can include it. It just hasn't reached the point of maturity where it's sort of integrated into the full sort of our waveform models using gravitational data analysis. So there's a lot of interest and a lot of recent work, but it's only really just kicking off now. People are really just working out how you can actually do this.
But once you have the PM Hamiltonian, what's the obstruction? I mean, it might be technical, but there shouldn't be any.
That's Mohammed. This is why I wish chat I got interesting. But that's going to arrive later today, so after probably it's much better than I do. Yeah, so I'm just going to quickly highlight some of the key features in V5, some of the recent highlights I think are of interest. So V5 is the latest generation of Hamiltonian from the AI group. This is our Simon and collaborators. This is just a big sort of text dump of things that are interesting. It does contain now most of the 5pn non-spinning terms, as Ricardo mentioned, and all generic spin terms up to 4pn. So you get spin orbit and spin spin, the next in order. Those get cubic and 40 in terms that lead in order. You do have improved NR calibration, use more NR simulations to help calibrate the CFD model than previous models. There is these test couple waveforms that are used in the calibration. So you use some Tchaikovsky solvers, particle dynamics, and then solve the Tchaikovsky equation, get the waveform, and use this to help us calibrate the model and further bring it down. I think the answer is nobody really trusts the spiral calibration of these test couple waveforms because you still like a lot of PM information, a lot of GSS information as well, especially in green spins. So this is still something where measuring nodes are okay. Nobody really trusts the spiral, but that's okay because you understand that. You get information from the orbit average generic calibrating, which I'll show in a few slides. Nice and this is partially processing information. So much more genuine physics included in the evolution. You get calibration of the non-spinning modes and radiation reaction use of recent results in second order gravitational subfaults. I'll show that in the next slide. And the procession equations, as I mentioned, are something expanded with subconsistent spin over and spin spin calculators up to next in the order. And there's some sort of caveats exactly on instance which states range conditions you choose and so forth. And it probably is fair to say that this is probably the most accurate assessing our model on the market. So 99.8% of cases do have a mismatch against these numerical simulations below 3%. Yeah. So in terms of this partial processing Hamiltonian, I'm getting that back to this. This is just a generic scheme. This is really adapted from slides by Tony Ramos-Valdez. Full credit for Tony these slides. We start with a full processing spin Hamiltonian. You form orbit averaging in plane spins, circular orbits. You can then sort of PN expand the UV equations motion. You also get the UV orbital equations motion in the co-processing frame. You can partially process the Hamiltonian to solve the standard Hamiltonian curve equations. You combine them into these co-processing frame waveform modes, and then you sort of get a full attrition frame mode to reconstruct the inertial frame in the waveform modes. I won't go into too much detail, but the fact that you have this partial processing information is really what's key. It's something that wasn't done in previous iterations. And it's something that is lacking in waveform models. We sort of do like genuine processing information and co-processing.
So then the procession isn't followed instantaneously. There's an effective sort of orbit averaging scheme. Yeah. I'm not saying that's negative. I just wanted to understand before it's kind of like they were doing everything instantaneously.
No, I think
it's very expensive.
That's right. There's orbit averaging. I think there's a point of view that they did check this. That it's okay and check the whole PM order.
If the differential equation not solved, then you are why you will not the average.
I think the reason they do orbit averaging is because they also want to apply a post-adiabatic framework to that Hamiltonian. But if you do the orbit averaging, you can certainly apply this post-adiabatic framework. So rather than solving the full ODEs and students analytical expansions or semi-analytical expansions of your Hamiltonian system equations, it's just a adiabatic scheme, which you couldn't do if you haven't averaged. Actually,
Yeah, but I mean, again, the adiabatic scheme, I mean, you're solving the differential equation, so just solve it. I mean, what's the problem?
it's much more efficient than the post-adiabatic framework. It's much quicker than the post-adiabatic framework. It's the computations.
You just factor me.
Yeah.
The problem is that they are solving. If only this could be cast in a more efficient scheme, this generation would be faster. It's very slow to generate.
Yeah, but if you didn't have this.
Yeah, exactly. No. See, the PA scheme is important. Yeah.
Yeah, you can come back to that. The other thing I just want to quickly flag up is that they do use this calibration of second order gravitational self-force. Here, gravitational self-force, you're really looking at the metric of the binary expansion in terms of mass ratio. The epsilon term is doing for you. I see a Schwarzschild metric, spinning. This is higher order corrections in this expansion in terms of these metric amplitudes. And you really can then go and construct the flux of the gravitational self-force in terms of these various contributions of the different orders. And you can match this to the EOV flux. If you do this, you find that you can then sort of go and compare your native EOV flux in blue and compare it to your GSF flux, black dots. These are the numerically evaluated GSF flux. And you can go and introduce a small calibration term delta, and this is then used to help correct the flux at high energies and extreme mass ratios. This thing you can do as soon as you have the GSF information, just numerical calibrations. It's a bit brute force, but it does work rather nicely. And then you just show that you can reproduce your input NR data rather quite explicitly, and things do look extremely good. Comparison between the different waveform approximates in terms of mismatches and leading mismatches and so forth. But just say the V5PHF does seem to be the most accurate currently on the market. There's then a bunch of slides that I put here, but I wasn't intending to discuss on model accuracy. This is just for reference materials. You can see definitions of things like mismatch, how things behave across the counter space. I think the only thing I can point out is that generically, as we go to high values of recession, mismatches tend to break down. As we go to higher mass ratios as well, things tend to break down. Otherwise, there's lots there for you to look at just to give you a sense of what I'm performing across the domain. But that's it. I'll come back.
Questions, comments?
So about using an R to fix unknown parameters, has this been validated at lower orders when you know the parameters, like 4 p.m. parameters? Can you get them accurately from an R?
I don't think people have tried to directly measure the parameters from in that sense. So you could play the game where you just use to get information to try to calculate the frequent term. You're still missing all the higher order information as well. So it's a bit blurred. So no, I don't think people try to do that. You just try to substitute your highest order analytical knowledge and then sort of calibrate where your ignorance.
I guess the main question that everybody would like to see answered is that, of course, the answer might be difficult to find. What is the PM order, self-force order that I need to reach to get systematic error under control, set signal to noise ratio, say 100? Given a signal to noise ratio, what is the theoretical fundamental extension of the model that I need to keep the systematic error under control? I understand you might not have an answer, but what is the way to answer this question?
I agree with this. I don't have an answer. One thing you can do, for instance, is look at things like these fluxes that you calculate. So here the blue is your highest PN knowledge, and also the black dots are your second order gravitational self-force. You can compare first order gravitational self-force against second order gravitational self-force against the MR simulations. So you can see how you really need second order gravitational self-force and higher to really match NR as you sort of approach the more comparable mass ratio regime, so really Q10 and below. You can see here exactly where you're deficient in terms of PN knowledge. You can see where you break it down.
So what is the y-axis here?
Oh, that's cut off. That's just the value of this rho coefficient, which is
Some figure that enters the way.
residual amplitude. Yeah.
And second support is known now?
So non-spinning, yeah.
Okay.
And this is exactly what they use to help tune the flux in your beam, is this knowledge of your second order non-spinning gravitational self-force. So this is one way just to see analytically where you're deficient in terms of your PN knowledge versus your gravitational self-force knowledge and mass ratio limit.
This is the Letiak work and other people who put in the second support.
This is Adam Pound, Niels Borben, and co.
Oh, Anna will be here next week.
Yeah, that's Adam is exactly the person who asked about this. I think he was lead author on the paper that produced the first waveforms, the second order gravitational self-force. Martin led the calibration of the second order gravitational self-force, but yeah, talk about it. He'll help you with certainly this question in particular. As to the other questions, I don't really have a good answer as to what PM order we need. There's other cases you can look at. You can look at, for instance, the scattering case where you compare numerical simulations to your PM calculations and see exactly how things look. See the convergence of, with 4 PM. There's some issues, especially in the spinning sector. So it's different cases where it includes spins or not. This is obviously difficult in itself.
So basically the best one can do so far is take some proxy of the waveform and see how it evolves with the PM with your parameters.
Yeah, precisely.
And then I guess.
Yeah, and I guess you also play the same game here, which is you just slowly sort of turn off certain aspects of the EUV model. I think, for instance, there are some higher PN spin terms that are available but not using EUV. And when I talked to the developers, they said it was just such a subdominant effect of mismatches, it just wasn't including the difference. Yeah, so I think you can sort of play around with changing the Hamiltonian by certain coefficients and seeing how the mismatches change in grade, just seeing which information is really most crucial here. I don't have that answer, I'm sorry.
Very follow-up question. I think it is really broad to do your infrastructure. Is comparable to some other. Let me just I'll rephrase my question, but don't answer it. This is provocative. As I'm looking at the EOB evolution over time, I always wonder: am I gaining knowledge for computational power, knowledge about what the physics in the broad system is, or am I just creating an interesting, successful computational program that gives me the waveforms at the end of the day? When I look at this flags in EOB, there is a very broader tool that's just there. But when you show us how to compute waveform, there's a whole bunch of other things that are going there. So this is where I'm struggling. As even the comparison, following Ricardo's question, even if a comparison there was successful or not, that's not necessarily translate directly to the waveform I'm going to get at the end of the day, which would be successful or not.
No, so I don't really agree with what you said, which is this comparison is a one-dimensional comparison, a huge amount of information, and it isn't really either exactly what is good is who, which sectors and fluxes are going to contribute is actually much more a good evolution for control of data. That's what it's giving improvement here. I don't know. I'm sure the developers have much better knowledge. You can look at instance of how the A potential compares to, for instance, the NR. Or the NR inferred potential, and you can see that the highest of the contribution really do make things. You do see that things lower, but with higher rate elevation, I should say, things can improve the state values. So there are some ways to help understand which sectors are contributing. You can also play the same game with blinded energies. The blinded energies in our simulations look at isolating blinded energy. In terms of the different contributions to spin sectors, spin orbits, spin currents, spin Q twins, etc. And you can sort of compare that then to which sectors are actually improved. So able to compare.
Thanks again, Geraint.
Now we update. Right?
Yeah, that's right.
Yeah.